This afternoon, in the programming models section, each one of us will be talking about several programming models that are supported for ALCF machines, most notably Polaris and Aurora. So for the next hour, I'll briefly touch upon the programming model called SYCL. I'm assuming that for this next 1 hour, folks would be a bit familiar with GPU programming models, um, uh, such as CUDA or some sort of some sort of familiarity with the GPU programming. So the focus will be on ALCF Polaris today. Again, we do apologize for not having Aurora just because of the maintenance, but you guys will have access to Aurora in due time. So most of the hands-on session and instructions would be specific to Polaris, and there are several stubs that are also provided to give instructions how to use it on Aurora as well. So feel free to look into that. So for the next hour or so, I'll briefly touch upon what is SYCL and how is it familiar with other programming models and where does it differ, and a few practical case studies and a bit of hands-on to just get familiarized. Talking about SYCL, it's a portable programming model to start with. It's mainly based upon C++, so it is highly motivated and draws several of its specifications from ISO C++. So if you're familiar with C++, you would see a lot of heuristics and abstractions, pretty much the same in SYCL. SYCL initially was motivated from OpenCL, so you would see that sort of several APIs as well, drawn from one OpenCL. The goal behind SYCL is to provide an intra-node parallelism. So it has nothing to do with the remote communication MPI. It is on-node parallelism model. We loosely speak SYCL as a programming model, but it is actually a specification. Similarly, like MPI, OpenCL, all SYCL is a specification, which means several vendors would take the specification and give their implementations. So there are several implementations of SYCL, and we would be talking about one such implementation of SYCL in the next few slides. The most important aspects of SYCL is it's a cross-platform abstraction layer, and it's heavily backed by industry, not just from Intel. We have several use cases from NVIDIA and AMD as well. It's open source, which is a good thing. So you could try develop what's happening in the SYCL file open source bugs if it is not working for you. And it's most importantly vendor agnostic. So it is not tied to a single vendor. Lastly, it is a single source model. So unlike CUDA or any other GPU programming models out there, you don't write a separate source code for GPUs and host. It's a single source C++ based source code that can run on both host and device. Device here means GPUs for the sake of context, and it could be FPGAs if you even have access to them. So it's a unified development model across all three vendor GPUs that we have in access today. SYCL is mostly maintained by Kronos Group. These are the gatekeepers. So Kronos Group also handles several of the other specifications just listed here, a few of them. So that's one thing to know about. So these are the few applications that have used SYCL in their code. So it could be SYCL directly or indirectly. So Cocos has a backend with SYCL. So Cocos is itself a portability layer, but if you use Cocos SYCL backend, it can still run on all three platforms. So it's a portability of portability. You can think of that way. So many of these applications directly use SYCL or use SYCL via Cocos or Raja as their window to access SYCL behind the scenes. So these are the few resources that I would like to share if you're looking into how to use SYCL and whom to ask questions. and specific documentation. So I would highly recommend folks to join the SYCL Slack. This is from Kronos Group, so you could post your questions. Most importantly, this is the GitHub link is the place where you can file issues if things are not working. Again, ALCF machines uses one or maintains one's implementation of SYCL from Intel. So it's called One API. You might have heard of this name in various terms. SYCL implementation from Intel is called One API or DPC++, or Data Parallel C++. So that is the implementation of SYCL by Intel. So SYCL, in other words, is just nothing but C++ with some SYCL standards and extensions. These extensions are not standards. These are just convenient functions requested by users, like from our ALCF facility or other sister facilities, that we need certain functionality that is missing in SYCL, and they appear as extensions. So these are readily implemented, so they have a quick turnaround time. So they are implemented by the vendors, and such that any application who have requested can use it. If these extensions are good enough and stable enough, they get ratified into a SYCL standard. So that's the process of why do the extensions exist and how they do get ratified into the standard. So talking about various vendors who are implementing SYCL, so as I was saying, Intel is one vendor that we are predominantly working with. So CodePlay is another vendor. So CodePlay is now absorbed into Intel, so we don't have two different implementations. It's all single DPC++. So it's based off of LLVM and open source, as I was saying earlier. It can work with any CPU. So you could run it on x86 or ARM. So you could run SYCL on any of these CPU platforms. These are the few listed supported GPUs that it can work with. So you can see all three major vendor GPUs are here. And in here, we have listed level 0. This is the name of the driver API used for Intel GPUs. Similarly, you have PTX as the display instructions or CUDA driver APIs. That's how it gets offloaded to NVIDIA GPUs, similarly for AMD. So all we are saying is, using DPC++ implementation of SYCL, we could target any of the CPUs and GPUs listed here. So this is a true compiler. So it's based off LLVM. On the other hand, we have a library. So there's a distinction between a compiler-based implementation and the library. So it's I wouldn't say it is not as feature-rich, but it gives all the necessary SYCL standards. So one has to implement all the SYCL standards to be compliant. So Adaptive CPP is one such implementation. It also targets various vendors and as well as the CPUs. So for the sake of this talk and for the ALCF machines, Polaris and Aurora, the DPC++ is the implementation that we'll be working with. This is a quick slide that talks about what are the distinction or the similarities between CUDA and SYCL. So to start with, how do you select a device in CUDA and how do you select a device in SYCL? So in CUDA side, you can select a device and you can supply the indexes. It could be 0 to 3 because we have 4 GPUs on Polaris from what we have heard in the morning talk. So there is no such device selection in SYCL. I mean, just by this abstraction, but it could select all the GPUs. So there is a fair bit of similarities between how do you select the devices. Memory allocations are pretty simple. So you have CUDA malloc, CUDA free. You have SYCL malloc device and SYCL malloc freeze. Data transfers are similarly. The APIs are exactly the same. So you have mem copies on both sides. Kernel launch is just syntactically different, but underneath the heuristics are pretty much the same. So you have the function name, the kernel name is my kernel, and with arguments applied. So it's just a way how you launch your kernel. So again, as I'm saying, like all the GPU programming models are exactly the same. It's just a syntactic sugar that differs. One important thing I would like to point out here is the streams. So many of the CUDA applications do use streams. These streams provide concurrency on the device side. Stream is inherently an in-order, so it is an FIFO, first in, first out. Similarly, we have a similar abstraction called SYCL. So this is an exact one-to-one equivalent of CUDA stream, only if you provide an in-order as a property. So SYCL does support out of order, which is the default, and in-order, which is an additional property. So if you want to port an application which has CUDA streams, you would use SYCL with an in-order property as an argument. There are several rich set of libraries from the CUDA side, and equivalently, SYCL has also matured over time and provides one-to-one equivalence. So all the Q math libraries, so which involves QBLAS, QSparse, Courant, anything that deals with the math, are included in one project called 1MKL. So you have GPU communication libraries called NICL on the CUDA. We have 1CCL for SYCL. 1CCL is at the moment not portable to all three vendors. It just supports Intel GPUs as of now. CuPy is a Python interface to the CUDA environment. So similarly, we have a DPNP, so data parallel NumPy, which you will hear in the next several talks in detail. So this is just a quick snapshot of how CUDA has one-to-one equivalence if you search for in SYCL. It's just a very simple syntactic differences that you need to consider. So these days, even if you have a single source code or a full project that you're looking forward to port, you would not port it by hand. There are tools that we could use, and I'll quickly show you how to use them. So as to minimize all the differences that we see between the programming language differences. For the next few slides, I'll talk about some of the abstractions in SYCL. So we have queues and contexts. So similarly, like CUDA streams, as I was saying earlier, queues provide a mechanism to submit work to the device or subdevices. So I'll talk about why I have subdevice here later in the slide. SYCL context is fairly overlooked abstraction. This is very familiar or very similar to CUDA context. So as like in CUDA, we don't use CUDA context so often. SYCL contexts are also not well exposed if you're writing a production level code, but they do exist for a reason. So CUDA context to start with, they are used for resource isolation or sharing, which means you can, using a context, you can share the resources or you can just isolate the resources to a specific device. So in simple words, if you have a multi-GPU, you can share a given pointer among all the GPUs via resource sharing. Or you could just isolate that given pointer to a specific GPU and not share it with others. So you could create a context specifically to that device. So your context has a visibility of all the GPUs or a specific GPU. So yeah, so a SYCL context can just consist of a single device. So anything you can work with is very specific to the device, or you can just have all the devices or a specific chosen of multiple devices. There are certain terms like root device and subdevices that we use. So these are not so complicated terms. It just means, are you using your GPU completely, or are you partitioning your GPU into several sub-GPUs? And we do use that in various contexts as well. So when you create or when you partition a device into subdevices, your memory gets partitioned, your resources get partitioned, and that's where all this partitioning resources or isolation of the resources comes into play with respect to the SYCL context abstraction. Talking about the most important aspect, which is SYCL, this is nothing but a CUDA stream. SYCL is a way to submit your job, to your kernels to the device, or you could submit your data transfers between host and devices. Okay, so SYCL is always attached to a single device in a possibly multi-device context. So even though you have context that can expose multiple devices or a single device, your SYCL is always tied to a single device. So whatever work you submit to the queue always get executed on that particular device. As like any GPU programming model, every work is asynchronous with respect to the host. So it's like fire and forget. So when you submit a kernel, it is asynchronous with respect to the host. Similarly, when you submit a data transfer, it is asynchronous with respect to the host. As I was saying earlier briefly, that SYCL queue can execute in any order. So the out of order is default. So it depends upon the runtime, the driver runtime or the hardware runtime to its liking to which task gets executed first. That is out of order. So if you don't want such a out of order like fashion of tasks, you can easily submit SYCL queues as in order, which acts very similar to CUDA string. So these are the two major software abstractions in SYCL that the one needs to be exposed to. So how does SYCL queues work between out of order and in order? So this is a quick snapshot. So if you create a SYCL queue and say I'm targeting a GPU, we did not specify any property here. So by default, it will create an out of order queue. So here is a DAG, okay? So first we start with A. BNC kernels can run in any order. And finally, we consume BNC results to run kernel D. So if we start launching an out of order kernel, out of order queue, so it could execute an A, B, C, D or A, C, B, D order. So there is no ordering between BNC kernels. It's up to the hardware to choose. If you need ordering and you need to use in order property, and depending upon the submission of kernel. So let's say you first submitted kernel A, it gets executed first, then B, then C, and D. So it just depends upon the order you submit your kernels. And that's the same order it gets executed when you have an in-order property. So that's the simple differences between an out-of-order queue and in-order queue. So if you're porting from CUDA to SYCL, I would just pay attention to how my queue gets created. Because if you get a wrong answer, the most likely culprit is you did not have an in-order property, and that's where all the concurrency differences came from. As I was saying, devices and subdevices in the earlier slides, SYCL has a concept called subdevices, which nothing means on the CUDA world big mode. So you can have multiple instances of a single GPU, a physical single GPU. The same paradigm or concepts do apply as SYCL subdevices, or if you're familiar with OpenCL, you have OpenCL subdevices. So we do use these two terms called explicit scaling, which means that you take a device and then partition it, and then use those partitions as virtual GPUs. That means it's implicit scaling. It means you just use the same GPU without partitioning as it is. The reason why we do partitioning of the GPUs is because your application workload is too small to take a full advantage of the GPU. So you partition the GPU into multiple partitions and you run multiple instances of your application on that particular GPU such that you increase the occupancy on that device. Or otherwise, if your GPU or if your application is heavily bound with memory and compute, you don't need to partition device and just use as it is. So this is a quick code or snippet how you can query. Can I partition my device or not? So this just applies to all the GPUs. So you could query for Intel, NVIDIA, and AMD GPUs. So you just select the platform, select the GPUs. In a given platform, think of it as a node, and you just query, get all my GPUs on that particular node. So you have a list of vector of GPUs. So you just loop over each of them and ask, can I partition it? So if it is partitionable, you can just create a new device just by using create subdevices as the API. So this is the way you create subdevices, and for each subdevice, you create a queue. So I hope you follow that from a node, we went into the GPU, and for the particular GPU, we partition it, and for each partition, we create a queue. And using this queue, we just submit all our kernels and the data transfers. On the implicit scaling, where we use the GPU as it is, we just query for the device and don't partition it, and we create queues for the entire GPUs without partitioning it. There's one more concept called SYCL events. These are similarly like CUDA events. Um, so these are used particularly for bookkeeping. As I was saying, majority of the operations on the SYCL side are asynchronous. We need to keep a tab on, is my kernel finished or not, or is my data transfer completed or not? So for those bookkeeping tasks, we do keep SYCL events. So any API that you come across in SYCL has a written parameter called events. So I just showed you the APIs for the data transfers. So this is a mem copy. It can be between host and device, or it can be a kernel launch, which is shown here, PAL4. So as you can see, event is the return type. So using this event, you can keep a track of whether my particular operation that you've just submitted via the queue is finished or not. Similarly, it's the same as CUDA events. So coming to the question of how do I port from CUDA to SYCL? So first we need to know about what are the equivalents between CUDA and SYCL. So we have threads, blocks, and grids on the CUDA side. Similarly, we have a very equivalent terminology called work items, work groups, and ND range. Similarly, like a grid is an array of thread blocks, and a block is an array of threads. Similarly, like ND range is a collection of work groups, and a work group is a collection of work items. So this is the hierarchy, and this is the one-to-one mapping between CUDA and SYCL. Talking about memory, there is no, again, any difference between CUDA and SYCL memory model. Similarly, like you have a global memory, shared memory, and register memory. We have global, local, and private. It's just a naming difference. And the heuristics are also exactly the same. So for the register memory, each thread is local to it. Similarly, we have work item, which is very local to private memory. So this table shows, and again, this table is available in the SYCL specification. The link is here. You have allocation types, which is device, host, and shared. As the name itself says, that device allocation first has allocation on the device. Host means it has allocation on the host, which can be a CPU, but it has access to device as well. So the columns accessible by and migratable to are slightly advanced versions of it. But when it says SYCL malloc device, it first allocates memory on device. SYCL malloc host allocates memory on the host. Think of it like as a pinned memory on the CUDA side. Shared is nothing but like a UVM memory. It's accessible by both host and device. It's just not, the initial location is really not known because it's of a lazy allocation. If the particular memory is being accessed on the CPU, the allocation gets first pinged on the host. So it just depends upon where you are accessing the memory from. So these are the three types of memory allocations in the memory model. As I was saying, the APIs are pretty much the same. You have CUDA malloc targeting the GPUs. Similarly, you have CUDA malloc device. The syntax is very C++ based. You can see that the queue parameter is passed all over the SYCL APIs. That is what or how you interact with a given device. So any allocation, data movement, or kernel launch accompanies a queue, which in turn is tied to a GPU. Unlike in CUDA malloc, you just set CUDA set device, which activates the device. But in here, we use a queue that we pass around for all the APIs in the SYCL. So this is one tricky aspect when you're porting from CUDA to SYCL. So this is just things to remember. On the CUDA side, you have XYZ as the indexing pattern. When you port your exact CUDA code to SYCL, you need to index from 210. The differences is because CUDA is C based and SYCL is C++ based. So it just depends upon which is the fastest index that is moving. So, and that is the reason why we have these differences between why we need to flip the indexing. So this is a very textbook example of how we use SYCL and very traditional textbook example of vector addition. So there's just one header, SYCL.hpp, that you need to include. As I was saying, this particular code looks like a C++ base. So you have arrays and namespaces. So these are nothing but C++ based. So if you omit SYCL header, it just acts as a SYCL API, a C plus standard traditional C++ base code. This is an example that shows how we perform computations on a GPU and how do we handle memory. So if we create three arrays, A, B, and C, these are created on the host. And we expose these A, B, C into the device using buffers. Okay, so we wrap A, B, and C arrays as buffers because using buffers, we access it in the SYCL device. So we wrap A, B, and C arrays using buffer A, B, and C, and we access them. So as we know that we perform a computation C equal to A plus B, A and B will be only read and C will be written. So you could provide certain hints to access these buffers. And these three lines shows the kernel launch. So instead of triple chevron, you just launch it with parallel 4. You could just name, this is a naming of the kernel. So you could just give any name. And this is the range. So we just want to loop over 1024, and this is the index. So if you're familiar with CUDA kernel launch pattern, this is pretty much the same, and as like any GPU programming model. And at last, we just print the results. So here we don't do any explicit memory transfers. That's the stark difference between CUDA and SYCL. And this is one such implementation called buffer memory model. This is not so well used because we have a very similar equivalent like CUDA using pointers. But that I'll cover in the next slide. But this is one such memory model where you don't explicitly do data transfers. So if you're accessing the data on the device, the buffer A the runtime will automatically move the data transfers for you. So A and B, since they are read, they move to the GPU. And since we are accessing C on the host, the runtime would move the data from device to host. So there are hidden data transfers behind the scenes. It's for ease of writing the code, but it comes with a lot of baggage of how do we manage data transfers. So if you're writing production code, you might get into unnecessary data transfers. So one should be very careful when using SYCL buffer as the memory model for SYCL. Talking about the famous USM memory model, this is very familiar like pointers, has one-to-one equivalence in CUDA as well. So similarly, in the previous slide, we create host pointers. We initialize with some data. We create a queue. These three would show the memory allocations on the device. So we pass the queue. We create memory on the device, A, B, and C. We copy the data from A to A and B, such that device A and B are valid. We launch the kernel. We copy the results back to the host, and we just print the results on the host. So this is a very similar memory model like CUDA, unlike SYCL buffer memory. So it has, in this, the difference between SYCL buffer and SYCL USM memory model is explicit data transfers. Here we explicitly say where to move the data between. In the buffer memory model, it's done by the runtime. So this is one slide that I'm just showing that how do you use in order property such that you can have one exact functionality like CUDA streams. So if you don't have an in order property, your memory transfers can launch after kernel gets launched. So you could just purely running a kernel of garbage data. So we need to ensure that A and B just copies first and then launch the kernel. So that's the reason we use in order as the queue property. So this is a slide that shows how do you access Polaris, what modules to load to get the SYCL module, and I'll quickly show you how to get a compute node, load these modules, and run some examples. Similarly, I should point out that ALCF Polaris is an NVIDIA-based machine, so we need to load a bunch of modules. So I'm using CUDA Toolkit 12.9, and this is the one wrapper for MPI as well. On ALCF Aurora, SYCL is by default loaded, so you don't need to load any explicit modules. If you just do module restore, it'll load all the defaults that you need. This is one slide that I'd like to point out that SYCL, as I was saying, is a portable module. Is there a question? Okay, moving on. So this is the way that you compile source code on the NVIDIA GPUs using SYCL. So one important thing is if you omit all the flags of FSYCL, this would act as a traditional C++. So Clang is a traditional C++ compiler, but it can compile SYCL code only if you pass certain SYCL flags. This applies to all three backends. So if we passed here FSYCL targets and saying that we target NVPTX backend, indicating NVIDIA GPUs, and you can even say what GPU architecture that you would like to target to. So this is ahead of time compilation. So this way you could target NVIDIA backend. Similarly, if you're targeting a ROCm or a HIP GPUs, you could do similarly exactly the same. We just briefly talked about SYCL, and it's not complete without the library support. So there are several libraries that are in the OneAPI ecosystem. So I was saying level 0 is the driver API behind the scenes for SYCL to target Intel GPUs. 1DPL is an equivalent of parallel STL library. So if you use Trust, or the recent days NVIDIA calls it CCL, the equivalent of that is 1DPL. cuDNN equivalent is 1DNN, and similarly, like Nickel, we have 1CCL. There are other libraries. One important library is 1MKL, which has all the math kernel math routines in it. So porting to SYCL, it's not straightforward to port from CUDA to SYCL without the library support. So 1MKL has several parts. So you might hear 1MKL from Intel, which is a product version. It is closed source. It can run only on Intel GPUs. But there is another open source version called 1MKL interfaces. Again, this is based off of the same MKL API, but this is open source targeting NVIDIA and AMD GPUs. So this 1MKL interface, if you're developing code for Aurora, you could just test it on any of your machines like ALCF Polaris or your cluster to just verify the code that is working and deploy it to Aurora. So that's the advantage of having an open source project. Again, you might get confused between MKL and 1MKL interfaces. That's the difference. And 1MKL is a product version specifically to Intel GPUs or Intel CPUs. 1MKL interfaces is a project for targeting other vendors. So 1MKL has interfaces to, as I was saying, Intel MKL, NVIDIA to all the GPU math backend, and AMD all the math backends. SYCL also supports some generic devices. So you could run it on x86 as well as ARM GPUs. So this 1MKL project can work with both DP++ compiler, which is what we're talking about now, or the adaptive CPP. This is another implementation. So this is the one interfaces project. It has support for all these domains. SYCL Sparse Blast is still being developed. It's not fully robust, but it is feature complete. So if you're running into issues, it's again an open source project, so feel free to create tickets there. So again, this is one snapshot of how each of the domains gets piggybacked to the backend. So if you use 1MKL interfaces library, you can target cuBLAS, ROCBLAS via a thin wrapper. So you would get exactly the same performance as using any vendor-based APIs. But this one API, 1MKL interfaces APIs are portable. This is a slide that shows how do you compile using 1MKL project. So if you have a source code, you could just specify MKL and 1MKL path and the library. So you could either target the complete library, which includes all the domains. So you could just pass lib1mkl, or you could specifically target a given domain. So if you just use BLAS on CPU and the NVIDIA side, you could just pick these two libraries. The idea or intention is to just limit your static library size depending upon how you are building your library. So that's the difference between like your runtime dispatch and the static dispatch. How do you use 1MKL in CMake? So this is just a quick snapshot. If you already have 1MKL installed, you would use find package, link the entire library or a specific domain with the backend name. If you don't have, you can directly install with fetch content in GitHub, in CMake, and then clone the library, and you can link similarly, as I was saying. As this is an open source project, this is just a quick recipe of how you can build 1MKL and turn on which domains you want. I've just shown here that I'm turning on just the kube math libraries, just turning off all the rest of them. This is one example that you can clone from this website and run it yourself. Talking about 1DPL, this is another project. I was saying it's a parallel C++ parallel STL based library. So it's a C++ based STL algorithms if you're looking for an equivalent from Thrust APIs. Similarly, like Thrust API, the interface is exactly the same. So except that you have differences in the headers, and as well as one extra argument which says that run it on a specific device. Again, policy is nothing but tied to the queue. So if you are creating a policy, you need to create a queue and then bind both of them. So that way you're targeting a particular device. So this is, again, an example of how you use 1MKL. You allocate memory, you launch MKL APIs. You can similarly compile 1MKL for all three hardware backends. So Intel PVCs. So the bold flag shows the differences between each of the three vendors. So you have QMKL targeting Intel. You explicitly pass NVIDIA flags, or you pass AMD flags for AMD GPUs. If you're running 1MKL, if you're pretty curious of what cuBLAS APIs am I using underneath and all that, you could just use any of the cuBLAS logging metrics and run your SYCL code as it is. But it will show you all the cuBLAS APIs that are being targeted. Similarly, like RockBLAS, if you want to just have logging information, you could use all the RockBLAS, cuBLAS logging techniques for your SYCL code. Similarly, 1DPL, you can run this 1DPL similarly like an STD transform C++ based on any of the GPUs. And as you can see, the compilation instructions are pretty much the same. Coming to how do we port a CUDA project to SYCL? So the tool is pretty mature, so you don't have to handwrite any code, just to minimize errors to start with, and also minimize time. So I would recommend to take advantage of this tool. And this is, again, an open source tool, so you could build it yourself on any machine and then use it to port either a single file or a complete project to SYCL. So the porting strategy is you take a NVIDIA code, use NVIDIA DPC++ tool. It migrates into an intermediate source code. So this is not a fully productive SYCL specification compliant source. So it has SYCL headers as well as headers from DPCT tool. This is just to provide a first initial implementation that you could directly build and test it to start. So think of this as a version 0. So if you want a production level code, you need to remove all the DPCT namespace and headers such that it is purely SYCL based. So if you're porting CUDA to SYCL, this is just a initial version. It is not in any form production compliant, but you can readily test it and verify the results. Talking about the multi-GPU programming, since all our machines are multi-GPU based, so the question comes, how does SYCL help if I have multiple GPUs, and what are the different ways that I could use several programming patterns? I'll briefly switch to training here, show some hands-on examples. So I assume folks would clone the repository. Again, this is NVIDIA Polaris machine. So we have 4 A100 GPUs. I just verified with NVIDIA SMI. If you go to SYCL folder, there is a README which says, how do you get a compute node? How do you load the modules? So I would start with loading the modules.
Oh, Abby,
Yep.
I still see the slide 45.
Oh, sorry. Let me switch. Can you see my terminal now?
Yes.
Okay, thank you. Sorry, I'm running. I'll hurry a bit because I just have 15 minutes. So let me load the modules. These are the instructions for Polaris. Similarly, you could do this for Aurora. So I've just loaded all the SYCL-based modules. So this is the SYCL 1 API module, and this is the module for the MPI wrappers for the SYCL compilers. To verify that you have loaded the modules, just do a version check on the compiler. So it says it's a Clang-based, so LLVM, and it found the CUDA installation with the version 12.9. So now we know that our Clang is compatible with the CUDA version as well. So SYCL also provides, like NVIDIA SMI, a tool called SYCL LS. This is just list SYCL to check what backends I have. So as I was saying, platform is like a node, and it says that it has 4 NVIDIA GPUs. Under a given platform, we have 4 GPUs with their details. So there is no other backend that SYCL is enabled for. SYCL only targets GPUs for now. And you can change that as well. So you could target CPUs as well by changing some environment variables. So this way you can quickly verify if my SYCL is enabled or not. So there is a project called 9 SYCL of Hell, thanks to Thomas, who has put a lot of work in compiling 9 set of source codes here. So I would not build all of them, but I'll just show you how to build. So this is, and the instructions are in the README file. Okay, these are the instructions for Aurora and Polaris. So since we already loaded the modules, I'll use cmake build. So I created a build directory. So as you can see, I'm saying take C++ compiler as Clang because it has the SYCL in it from 1 API. And we are passing additional flags just for detecting CUDA backend. So I'm saying target SM80, A100s, and the CUDA backend via SYCL flags. So this would enable SYCL compilation and also add ahead of time compilation with the SM80 as the architecture. So if you do make verbose 1, you would see each of the .cpp file, which is a traditional C++ file, compiled with Clang compiler and all the SYCL flags that we have just passed. So this would ensure that your traditional C++ is now compiled as a SYCL program. Okay, just for the sake of time, I'll just do make J. Let's ignore the warnings for now. So we have 9 executables. I'll start with the first one. Let's look at the source code of the first one. Okay, as I was saying, this has a single header. It has a std vector, which is from C++. So you mix both C++ and SYCL. As I was saying, it's a single source. We would list the platform. I've just shown what is a platform from SYCL LS. And in that platform, we just list how many GPUs are there. So we get devices and we print the name of each of them. That's the simple logic. As you can see, I'm using std out. I'm looping over vectors. So everything is C++ based. So let's run the code. Okay, it says we have used NVIDIA CUDA backend as the platform, and 12.7 is the driver version. Since we have 4 GPUs, it just lists each one of them and says it's a GPU. So you can even query if a given device is a GPU or not. Okay, so if you get a device, you can query if it is a GPU or not by each GPU. So this is all part of the SYCL specification. So here we say devices. It doesn't mean that it's particularly a GPU. It can be CPU as well, or it can be an FPGA. So that's the reason we have several of these helper APIs like eGPU, eCPU, to just know whether the device that I'm working with is a CPU or a GPU. Parallel 4 is an example for kernel launch. Let's go to the first one. So as I was saying, we need a queue. Without queue, you cannot submit anything in SYCL. So with queue, you can query details. You can even submit a kernel. So this is a single task. This means that it will just use one thread to just run the kernel. This is like you could use on the CUDA side, if you launch it with one grid, one block size, one thread size, it's as similarly like that. It just use one thread and prints an hello world example. So let's run. Okay, so it says it's running on an NVIDIA GPU and it prints hello world. Here in this source code, we never specified which GPU to choose. So we have 4 GPUs. This queue can bind to any one of them. It depends upon just hardware. So the queue here picks one GPU out of the 4 and runs this kernel on it. So you can even be specific that launch kernel on that particular GPU only. So you could even do that just by using CUDA visible devices equal to, since there are 4 GPUs, I can just use 0. And when you run the same kernel, it would launch on that particular GPU, even though it doesn't say. But this way we can ensure that this particular kernel and all the information, all the tasks that you submit to the queue runs on the CUDA visible devices that you chose. Okay, going back to our small set of examples, memory. So we have a SYCL header, traditional header. So these are the snippets to access the input instructions. This is where the memory allocation is. So traditionally, we create a queue. We just do this in every example. We just print which device we are running. CUDA malloc shared. This means we allocate memory that can be accessed on both host and device. So global range is the size of integers. It's very C++ based. So we're just saying that create these many ints that can be accessed by the queue. And this is the pointer. So we launch a kernel and indexing this pointer. The question is, we don't know whether it runs on host or device. Okay. And then we just access this pointer and print out the data. Since we are printing, it'll be on the host, right? And we free the memory. So here Q, we'll just run this code and see where it runs, in fact. So it says it's running on NVIDIA, so which means Q is created on the GPU. Let me put the source code here. The queue is created on the GPU, but the prints are done on the host. So which means that memory is migrated here. So that's the advantage of having malloc shared. So the memory gets migrated between device and the host. It's for convenience, so we don't have to have two different pointers, but there are hidden costs behind the scenes. Talking about other examples, I'll briefly touch upon the 6th and 7th, which is in order and out of order queue. Okay. Again, the code is pretty simple. We create an in-order queue, specifically using this property, print the details. Here we allocate memory only on the GPU, so it is not a malloc shared. We access this memory in the kernel, okay? And we do some host allocation, copy the data, free the memory. The goal here is we are submitting a lot of work to the queue. So we create a queue with in-order property. A queue gets created and submits a kernel. We do a copy, we synchronize. So since we submitted this first, kernel gets executed first and then copies later. Unlike the other example, which is an out of order queue, we don't have an in order property here, but we have a queue kernel submit and as well as a copy. So if you launch this program, your hardware can decide to choose between whether should I copy first or a kernel first. If it copies first, you would be running kernel with garbage data. So that's the disadvantage with having an out of order property, but it could have several advantages. If your program or an application has a lot of asynchronous data, you could use out of order and can run it efficiently without forcing it to be in order. So these are very simple examples. Feel free to run them on both Aurora and Polaris. I'll just briefly talk about multi-GPU for the next 5 minutes or 10 minutes or so. How do we program multi-GPUs that we have using SYCL? So in a real application, can SYCL provide or exploit all 4 GPUs without using MPI? So yes, the answer is yes. We have SYCL, and this is a source code. The way we can get it done is we query for all the devices. So it gives us a vector. The vector size here is 4 because we have 4 GPUs. We just loop over all of the 4 GPUs just to get some basic info. Print what is the name of the device, who is the vendor. Here we create queues for each of those devices. As I was saying, with the queues, you submit work to the GPU, right? So you create queues for each of the GPUs. So you create the same size as the number of GPUs that you have detected, which is 4 in this case. You create 4 queues, and you submit your kernels to each of these queues. So when you submit to each of these queues would run kernels concurrently, and at the end, you just wait for all of them to finish. This way, you can program all the 4 GPUs in the single source code without MPI, with the help of queues that are tied to each of the devices that you have detected. So let's just compile this source code and run. The instructions are right here. Okay. Okay. So as you can see, we just found one GPU and the kernel ran on the GPU 0. The reason is we have set CUDA visible devices to just one GPU. We do this again. So we just selected one GPU. Let's unset this variable and run the source code. Run the example again. Now we were able to detect or see all 4 GPUs. This hello world gets printed by the kernels running on each of these GPUs. That way we can easily mask which GPUs to use at the runtime level without changing any source code. In any real production application on LCF machines, we need MPI. So the question is, can I use SYCL and MPI together? Similarly, like I use CUDA and MPI. So this is a simple source code which has a combination of SYCL, OpenMP, and MPI all in the same file. So this is a source code that is motivated from ALCF's Hello Job Step. The motivation or goal behind this example is, or the source code is, when you run an MPI application with SYCL exposing GPUs and OpenMP exposing CPU threads, how are they all coming together? So, so we use CUDA visible devices. We initialize MPI. We see how many GPUs from SYCL. We initialize OpenMP. And in the end, we just print all the information. Which MPI is using which OpenMP thread, which hardware thread, running on which node, what is the runtime GPU ID, what is the actual GPU ID, and what is the bus ID. So we just print a lot of information here. The goal of this example is to verify which MPI is bind to which GPU and which OpenMP thread or hardware thread is being used. So the compilation instructions are right here. So here we pass a lot of SYCL flags, which we have been seeing for the past 1 hour, and I have OpenMP and traditional MPICXX. So let's run this. Since there are 4 GPUs, I'm using 4 tasks, MPI tasks, and 1 OpenMP thread. Okay, so let's quickly show it again. I'm using 4 MPI ranks, 4 hardware threads. The hardware thread IDs are shown here. We use 1 OpenMP thread. So the ID of the OpenMP thread is 0. We are running on this current node. You could just do it for multiple nodes as well. The last 3 shows information about GPUs. So we have 4 GPUs with real indexes. And since we are masking each of the MPIs to only have 1 GPU visibility, the runtime GPU ID is naturally 0, but their bus IDs are unique. So this way you can verify if your MPI is correctly bound to the GPU or not. The reason why we bind is shown or briefly discussed by Victor prior to the lunch. This is to have concurrency between your hardware resources. So if you see NVIDIA SMI topo -m, it says GPU, all the 4 GPUs, and gives you a matrix. Your GPU 0 has affinity to the CPUs of these cores, and it falls on the NUMA domain. So if you're running on MPI 0, you're bound to GPU 3, but your CPU IDs are briefly incorrect because it is using 0. So you have, even though you're running your code, getting right answers, it is not really efficient because nothing is coherent here, because your GPU 3 is bound to thread 0, which is correct. But your thread bindings are wrong. So let's just quickly change and add one more last variable, CPU bind list 0, 8, 16, 24. Okay, now it says that your MPI, GPU binding, and the hardware thread binding are very coherent with the hardware. So it is very important that you have mappings between your MPI, OpenMP, hardware threads, and the GPUs, all mapping to the NUMA domains and such that it respects the NUMA architecture, so as to have the best performance. And these and the last two slides, I'm just showing what we have just discussed in the multi-GPU programming. And thank you for your time.